going to talk about the first 5 transition elements. First 5 transition elements. Now, we are looking at scandium, titanium, vanadium, chromium, and manganese. But let's start with scandium. Scandium is in group 3B, and we want to compare and contrast it with aluminium from group 3A. It is surprising how similar the transition elements are to their regular elements in the same group. This is group 3, aluminium's in group 3, and scandium is in group 13. And then we could say that the normal, so-called normal, the not transition, those without d electrons or available d orbitals in the regular group could be the n, and the n plus 10 would then be the B elements. However, let's look at the comparison between these first 5 transition elements. We're looking at scandium and aluminium. In solution, they both form a 3+ ion. For scandium, this of course means that the 4s electrons as well as the only 3d electron has been lost, which means that scandium has absolutely no transitional properties, no paramagnetism, not highly colored, it's completely colorless in solution. But what we're looking at is the comparison between the group A metal, aluminium. In solution, the cations hydrolyze significantly and give acidic solutions with polymeric hydroxo species. On addition of the hydroxide ion, the hydroxides of aluminium and scandium both produce gelatinous precipitates. These precipitates dissolve when you add an excess of base, and they give an anionic species. Both of the metals also form isomorphous compounds of the type Na3MF6, where M is either aluminium or scandium. And this is, we can say they are isomorphous here, and that means they are the same shape. Structures will be of the same shape. Not only does aluminium resemble scandium, this is the aluminium hydride. When hydrogen sulfide gas is bubbled through it, if you were to take the scandium hydride and bubble hydrogen sulfide through it, it would also produce scandium hydroxide. They also precipitate as solids. The hydroxide is a solid, and they are, once again, similar structure, similar shape. Now, we should look at titanium, and titanium is in group 4, or otherwise known as group 14, and it has a lot of comparison with another metal in group 4A, and that is tin. So we can say titanium and tin are very similar. If we start with the oxides, the most common oxide of titanium, the white powder, the well-known white powder, titanium 4 oxide, we also get tin 4 oxide. Same shape, same form, isostructural, and both of them will turn yellow on heating. So they're isostructural, and unusually both turn yellow on heating. So they behave in very like manner, so many of these compounds. Melting and boiling points are also very close, and the chlorides of these both behave as Lewis acids in solution, the hydrolyzing water. Let's have a look. Titanium 4 chloride. Hydrolysis means it reacts with water and it will then form the titanium 4 oxide and HCl. Not necessarily balanced there, but that is what happens. And in like manner, tin 4 chloride, hydrolyzing, in other words reacting in water, will form the oxide, the tin 4 oxide, and hydrochloric acid as well. So they behave in very, very similar manner. When we go on further, as we look at phosphorus, phosphorus is in group 5A and vanadium in group 5B, or otherwise known as group 15, group 5 and group 15. Now here we find that phosphorus is a non-metal and vanadium is a metal, but there are still some striking similarities, particularly in their +5 oxidation states. The phosphate ion, PO4 3-, and the vanadate ion, VO4 3-, are isostructural, and they're both strong bases, and they also, both of these elements form a large number of polymeric anions. That means more than one of everything. For example, quite a rare one is P4O12, 4-, and vanadium forms the equivalent V4O12, 4-. So even in these unusual anions, polymeric anions, they are similar, they are isomorphous and isostructural. Sulfur and chromium are the next. Sulfur is in group 6, 6A, and chromium in 6B, or otherwise known as group 16. Even the physical properties of some of these compounds are similar. The oxochlorides, sulfuryl chloride and chromyl chloride, are very similar. Sulfuryl chloride is SO2Cl2 and chromyl chloride is CrO2Cl2. That is chromyl and sulfuryl chlorides. And they have similar melting points and boiling points. They both decompose in water in a similar manner. They form chromates, dichromates, and sulfates and pyrosulfates, but these differ. The chromates and dichromates are strongly oxidizing. Chromates, so they're similar in structure, chromates, dichromates, compared to sulfates and pyrosulfates. So they will have the same oxidation state of the central atom, the same number of oxygens, the same structure, but the properties are different because chromates and dichromates are strongly oxidizing, and the sulfates and pyrosulfates are non-oxidizing. Another difference, of course, is the sulfates and pyrosulfates will be colorless, and the chromates and dichromates are highly colored. But this, of course, has nothing to do with being a metal and a non-metal. This is because there are d electrons in transitional element which are completely absent in the non-transitional elements. Finally, in this group of elements that we're looking at, the first 5 in the first series, we get manganese, and chlorine is in group 7A and compares surprisingly with manganese in group 7B or group 17. Manganese in group 7B, otherwise known as group 17. Now chlorine once again is a non-metal and manganese is a metal, but the oxoanions are both in this case strongly oxidizing. The perchlorate Cl O4- and the permanganate MnO4-, both of these elements are in the +7 oxidation state, which is highly reactive, not terribly stable, and very useful as an oxidizing agent. The salts are also isomorphous, meaning they are the same shape. And once again, the permanganate and the manganese ions will all be highly colored, whereas the chlorine counterpart will not be because there are no d electrons. The oxides are also comparable. There is an unusual oxide with a +4 oxidation state which exists for both chlorine and manganese, and both in similar ways, ClO2 and MnO2, giving them a +4 oxidation state. And the interesting thing is they are both stable, although this particular one is a gas and this is a solid. This is a black solid, this is a yellow gas, but once again the same oxidation state, the same isomorphous shape, and the same tendency. So it is quite surprising, the comparison between the A group and the B group, and it makes an interesting study as our start to looking at transition elements.